to include the effect of source convection and showed that at very high jet velocities, the noise power scales at the third power of jet velocity, which is a very important result. Then there is the famous Fox-Williams-Hawkins equations, which is widely used to predict airframe noise and jet noise from computed flow fields. And finally, there are many other things which you'll be hearing from the other presenters in the next 3 days. Professor Fox-Williams made a systematic study of crackle, which I'm going to address in a greater detail here. Now, crackle is a subjectively different phenomenon, a component of noise which is not seen in spectra, which came to the forefront during the development of the Concorde in the early 70s. And this is caused by random strong compression waves followed by gradual relaxation. Now, Professor Fox-Williams and his group noted that crackle was already present in the near vicinity of the jet and proposed that the origin of the crackle was due to nonlinear steepening of the source, which is not directly connected to nonlinear wave steepening due to propagation over very long distances. Thus, these two, or crackle and nonlinear wave propagation, are two distinct phenomena, though they share some common characteristics. Now, they also developed a criteria for identifying crackle. That is by looking at the skewness of the time signal rather than at the spectral measurements. For low subsonic jets, the skewness values are found to be much below 0.1, whereas for cracking jets at higher velocities, it was always greater than 0.3, and values as high as 1 or 1.5 are measured close to the jet for the Concorde engine. My interest is not in crackle per se, but I came across something unusual when I was trying to reconcile some differences between model scale data and engine data, and that's what I'm going to be talking about in the rest of my presentation. These are some Australian pictures taken by Yulu and his group at the Florida State. You have a Mark II perfectly expanded jet at various temperature ratios, and cold jets produce a velocity of 500 meters per second at very high temperature ratios of 4.3. You have velocities in excess of 1 kilometer per second. Now, they also have the random appearance of random waves close to the jet exhaust, denoted by the green arrows, and that is seen to appear at high jet velocities, about 877 meters per second. In the other high velocity case, the frequency of occurrence of these waves are found to increase with jet velocity. And these are good physical photographs of the occurrence of these random waves. Now, I conducted a series of experiments to understand some nonlinear propagation, and all my work was done at the Boeing Low-Speed Aeroacoustic Facility, or LSAF. This is a free jet wind tunnel. Okay, this is a jet simulator which can produce two streams of heated gas to simulate high bypass ratio turbofan engines. And this whole thing is embedded, the jet simulator is embedded in a free jet wind tunnel, which can get to a Mach number of 0.32, which is higher than the takeoff speeds for most of the aircraft in service today. Also, this jet simulator is incorporated with a 6-component force balance so that you can measure thrust alongside acoustics at the same time. These are a series of microphones mounted on towers, and as per Boeing convention, the angles are measured from the forward or inlet axis with 50 degrees to 155, which is close to the jet axis where jet noise usually peaks. Now, for this particular set of experiments, I had 4 microphones at physical distances of 10 feet, 16 feet, 22 feet, and 30 feet at an angle of 150 degrees, which is 30 degrees from the jet axis. And let me show you some typical spectra which you have seen. This is for a cold jet, Mach point 0.7, with an acoustic Mach number of 0.67. And as you go further, as the distance increases, the amplitude drops. That's what you see here. And these are the subsonic nozzle was a 2.5-inch diameter nozzle, whereas the CD nozzle for the supersonic case was 1.25 inches. And these are the R/V values for the different nozzle distances. Now, we tried to normalize the spectra by correcting it to a standard distance of 20 feet, as well as to standard day conditions of 77 degrees Fahrenheit and 70% relative humidity. Now, you have a Mach 0.7 cold and heated, but for some reflections from the exhaust collector, which is closest to the fourth mic, you get epsilon within about a dB at all frequencies, especially at the higher frequencies. That is, you can assume linear propagation and you capture the 1 over r² spreading, which is what you expect and which has been done. Now, when you go to the supersonic jet, Mach number 1.9, you do the same exercise, you see that there is higher amplitudes at the higher frequencies. That is, as you go further away, there is increase in the amplitude at the higher frequencies, and this is due to nonlinear propagation. And you also see reduction in terms of energy from the peak to the lower and higher peak other sides of the spectrum. The important point to observe is that there is nonlinear propagation. This data cannot be captured by 1 over r squared. These are all data well established. Now let me show you something new and totally unexpected. This is a Mach 0.9 subsonic jet, cold jet, and heated jet. For cold jet, you get excellent collapse at the highest frequencies. But for the heated jet, you start seeing this nonlinear propagation. Now, what is different between these two cases? The only thing that's changed is the convective Mach number, and that has become slightly supersonic for the heated case. Now, the question that needs to be asked is, does this happen suddenly, or is there a gradual progression to nonlinear propagation as you increase the convective Mach number? By the way, it's been observed experimentally that a value of 70% of the free jet velocity well represents the convective velocity of the large-scale structures, and that's the value used in the computation of the convective Mach number. So what I'm going to show next is the progressive increase in the convective Mach number. We have the jet heated at a very high temperature ratio of 3.2, and you increase the Mach number from 0.6, 0.7, 0.8, 0.9 to 1. And this is at an angle of 145 degrees, which moves the microphone away from the collector. There's no reflections from the collector. The black one is the closest microphone, which is at a distance of 16 feet, and the red one is at a distance of 26 feet. So again, we do a collapse using 1 over r squared spherical spreading. And at the lower Mach numbers of 0.6, 0.7, 0.8, you get excellent collapse within a dB or so at the highest frequencies. But when you go to Mach number of 0.9 and 1.0, there's obviously a distinct difference in the two spectra, where you see the amplitudes being higher at the farther microphone. Again, if you have listed the convective Mach number and above a value of 0.8, it becomes slightly supersonic. Now, it's been traditionally believed that you need to have a very high amplitude to have nonlinear propagation. And this is the overall sound pressure level measured at a distance of 78 diameters and starts at 110 dB for the lowest Mach number case. And there is not a big jump of only 4 dB between when you change the jet Mach number from 0.8 to 0.9. So I want to propose that somehow the nonlinear propagation doesn't seem to be tied to very high amplitudes, but it is well represented or well quantified by the convective Mach number for jets, which is totally unexpected, and this is some of the reasons why we're having problems trying to collapse model data with engine data, which I'll address in a future conference. Now, if you look at the skewness values as suggested by Shon, for the very low subsonic jets, the skewness values are well below 0.1. But once you cross, this is a Mach 0.9 subsonic jet at a very highly heated temperature ratio, the skewness values jumps to roughly about 0.3, which is the criterion established by Shon for the onset of crackle. So let me make some observations. Heated subsonic jets exhibit crackle-like features, and surprisingly, the overall sound pressure level does not seem to be the controlling parameter for the onset of nonlinear propagation. However, the convective Mach number seems to be a good indicator for quantifying nonlinear propagation. When the convective Mach number is less than 1, you have linear propagation and low skewness values typically of the order of 0.1 or less. But when the convective Mach number goes slightly supersonic or above supersonic, you have nonlinear propagation and the skewness values 0.3 or above. Now, this trend has not been picked up for over 50 years of jet noise research. It was really surprising to me, and I would like to offer this as a tribute to the great work of Shon, and I would like to pose these following questions. What is the physical mechanism that causes nonlinear propagation when the convective Mach number becomes supersonic? And what kind of flow characteristics would we see if we could get a detailed picture of the flow? So now to the title that Euler gave me, recent advances in noise suppression. We'll move on to more practical matters. This is the source of aircraft noise. You have the engine noise, which consists of jet noise, combustion noise, and fan and turbine noise. And you also have airframe noise, which is caused by the flow over the discontinuities like the flat side edges, landing gear, etc., which is all lumped together as airframe noise. This is a typical breakdown of the different components for a commercial aircraft powered by high bypass ratio jet engines, which is typically about 5 to 6 for modern day turbofan engines at takeoff. and the y-axis is a decibel scale. And as you see, the jet noise is the dominant component. Then you have fan noise, airplane noise, and turbo noise. And this is the total noise. If by some miracle you can wave a magic wand and get rid of the airframe noise at takeoff, the total reduction in noise would be probably about 0.1 dB. So we need to reduce the jet noise in order to get a perceptible difference in noise reduction. Well, okay, let me get you oriented on the aircraft certification procedure. Some of you may not be familiar with this. The noise metric which is used to quantify flyover noise is the effective perceived noise level, or EPNO. Now, this is a sketch of a plane landing here. You go down the runway, you push the throttle to max power, climb, and then you reduce the throttle. There are 3 different measurement points. One is called the lateral, and third one is flyover. There are 2 measurement points at takeoff and 1 at landing. Now, the lateral noise level is the hardest to control because that's defined as the level at any altitude for the plane where the noise level peaks. So, and the microphone is located at a lateral distance of 450 meters from the center line of the runway. So that's the hardest nut to crack, so to speak, in terms of noise reduction. Whereas at flyover, once you get a safe altitude, you can pull back the throttle, reduce the engine power, thereby reducing the noise that gets to this cutback or flyover microphone. And you also have one at approach. So I'm going to concentrate mostly on takeoff noise because at approach, jet noise is not the dominant component, since fan noise and airfoam noise are equally important. Now let's look at a progress in noise reductions in the history of aviation, right from the early 50s. These planes, these are all the planes that have ever been built and flown. It starts with the 707, etc. And these are the red ones, are the early planes powered by the turbojets and low bypass ratio turbofans. Then you came to the first generation of the high bypass ratio turbofans in the early 70s, especially for the 747. And the bypass ratio jumped from somewhere around 0.3 to about 5, and you saw a dramatic drop in noise. In the last 25 years, there's been very little jet noise reduction, and most of this noise reduction has been achieved by fan noise reduction, where you have made improvements to the nacelle and the lining and the fan designs. So if you draw a straight line to this cluster of points, it's somewhat flat, and the only plane which I want to point out is the 777-200 with a GE engine, which is about 6 dB quieter than the Pratt and Rolls-Royce engines because the bypass ratio was again increased from 5 to 8. So all I want to point out from this is it's extremely difficult to reduce jet noise at a fixed bypass ratio, and that's our challenge. Now let me show you a montage of different planes, Boeing planes. This is the 67, this is the 37, and 2 views of the 47. You have a fan flow here, and you have a core nozzle. Sometimes you have an external plug, but most of the cases it's buried inside. But the engine architecture looks quite similar for all the planes, and you can put up a picture of the Airbus planes also, and some of them look exactly the same. Now we can visualize this in a simple way. You have the hot core flow surrounded by cooler fan flow here, and you have an inner shear layer between the primary and secondary flows, and there's an outer shear layer between the fan and ambient flow, and finally you have fully mixed jet. So if you have to construct a model of the jet noise, you could look at this as 3 different sources. Now we need to understand the importance of different sources with regard to their frequency and directivity content, and this has been studied for the last 30 plus years at various universities and industry and NASA. We know that the secondary shear layer is responsible for the production of high frequency noise at all angles for a high bypass ratio turbojet engine. And the mixed jet, which is further downstream, produces the low frequency noise, and the primary shear layer is responsible for the low to mid frequency noise at aft angles. So typically, jet noise peaks at aft angles, and if we want to reduce jet noise, we need to modify the inner shear layer. So how do we do this? Very simply. It's a bevel nozzle, and this is single bevel nozzle, and this is a dual stream nozzle. Oh, only the primary nozzle beveled. And to give you pattern spending on this, I've tested 2 different bevel nozzles of bevel angle 24 degrees and 45 degrees, and the bevel angle is given by theta on this. And this is the azimuthal angle. As you look from the back to a single nozzle, you have 0, 90, and 180. 0 is on the ground, 90 is up to the side, and 180 is up in the sky. And this is the inlet angle. Now, I would anticipate significant azimuthal content for this because your exit profile, when you look from the end, is not circular. It will be some form of oval. So we need to map the azimuthal content of this nozzle. So for this purpose, let me go back. Let me show you a close-up of this Boeing 747. What I'm proposing to do is leave everything alone and just go and bevel the primary nozzle alone. And there are very good reasons for doing that. The nacelle is a very expensive part, and redesigning that would require optimizing the engine, pylon, wing mount, and etc., reduction of drag. And as a noise solution, as a non-starter, nobody will buy that. So this is a simple concept we're proposing here. And let me just briefly show you this. So for this case, since we want to map the asymptotic directions, I have a set of microphones exactly at 90 degrees, the same height as the jet center line, and also another array at 30 degrees displaced downwards. So for a bevel nozzle, I would do a test with the bevel pointing towards the ground, so I map out the noise at azimuthal angles of 90 and 60, and rotate it to get 0, 30, rotate it the other way to get 180 and 150, so that I can map the azimuthal content of the noise for this concept. What happens to the aerodynamics? The thrust axis lifts off because flow is flowing up now. So you have an axial force red, the thrust axis is blue, and you introduce a normal force. Now the deflection angle, what I've found is only a function of the bevel angle. So once you cut the nozzle at a certain bevel angle, it's not a function of the pressure ratio, which is very encouraging because you can modify this nozzle to align the thrust axis with engine axis. I told you we have a 6-component force balance, so I can measure all these components and calculate the deflection angle, which is what I've done. And most of the thrust loss we've associated with this nozzle is due to this cosine effect of this red, which is not the blue, which is the thrust axis. Now, one can reduce this by drooping or tilting this nozzle, or contouring it. So all you take this, instead of cutting it this way, you contour it so that the plume is again directed, aligned with the engine axis. And that way you can recover the thrust loss associated with thrust vectoring. Now, what kind of loss are we talking anyway? This is a typical takeoff power high thrust with a primary nozzle pressure ratio 1.9, and the dark circles, and I've made a sweep at the secondary pressure ratio, or the fan pressure ratio here. The dark circles, and okay, let me also point out that the y-axis, each division is 0.5% of thrust. So for the conventional or round nozzle, round and round, you get this variation, you get about 0.99% of thrust. With a bevel nozzle of 24, you lose thrust by 0.25% or less. With a bevel 45, it's much larger, it's 0.75. Of course, that's what you would expect because the plume is lifting off. So at takeoff power, the thrust loss due to bevel 24, even if you do nothing, is less than 0.25%. Now that's a takeoff, but we're not too worried about, as a commercial company, about takeoff thrust, but cruise thrust, which is where most of the fuel gets used up. And that's where you have to minimize the thrust loss. Now, for most of the commercial engines, the pressure ratio of the core is 2.4, and the fan pressure ratio is roughly about 0.6. So when you look at the bevel 24, the thrust loss is even less, of the order of 0.2. And as I've mentioned, this can be further mitigated by proper design. Now, what kind of noise do you get? Let me show you the typical result from a single bevel cut. This is the red line is the equivalent round nozzle. So I've calculated the noise for a pie shape with 30 degrees in the azimuthal plane and integrated all frequencies or all angles in the polar direction. And this is a variation you get for total noise power. 0 is being on the ground, 30, 60, 90. So it's obvious that you get a 4 dB reduction in power on the ground just by beveling the nozzle. And it peaks somewhere near 90 degrees and starts dropping. But if you look at the overall power level, you get only a 1 dB noise reduction at a very high Mach number of 1 unheated. So it's nothing to write home about. So what we are using here is you have asymmetric variation of noise around the periphery of the nozzle, and we exploit this feature to gain noise reduction on the ground. And this is the beauty of this concept. Okay, let me show you some sample spectra here between conventional round and round and the two primary bevel nozzles. Black is the baseline, the red is the bevel 45, and blue is bevel 24. As you know by now, bevel 24 is the winner, and you don't see any increase in noise for bevel 24 at any angle. And at low angles, you don't get any noise reduction, but if you go to the peak noise reduction, you get substantial noise benefit of about 4 dB across the spectrum. The other thing I want to point out is there is no crossover or increase in noise at the higher frequencies, which is the bane of all the other mixing device-like concepts which have been tried in the past. You get a noise reduction in the low frequencies compounded by noise increase at the high frequencies with a net reduction of nothing. Now, let's skip this. Okay, now this is the cumulative noise benefit. This is in terms of the delta EP and dB, which is the round minus bevel, as a function of azimuthal angle at various free stream Mach numbers. This is at 0 angles, 30, 60, 90. Again, you need to look at 2 different measurement points at 0 angle for flyover or cutback, and the sideline lateral microphone, which would be a sum of these 2 noise benefits you get at these 2 angles. As you can see, you get about 2 to 2.5 EP and dB depending on the takeoff speed and the azimuthal location of your observer. Now this shows the cumulative noise reduction at takeoff, which is the summation of both the microphones, lateral as well as flyover, for the 2 bevel nozzles. At a free stream value or static, when the plane is sitting on the ground, this bevel 45 gives you an extremely large noise reduction. However, when the plane starts moving forward, it drops. But for the bevel 24, which is the better concept, you get about a 4 EP and dB reduction during takeoff with a thrust penalty of less than 0.2%, which can still be reduced. Now let's do a simple exercise to see what it does. Because of the sign of the vertical component, you have a lift loss. Now, let's estimate that for a typical L/D for cruise, for most of the aircraft, is 17.5. The plume deflection is 2%, sine of 2 and cosine of that, and you have for 1%. So the lift loss for the same L/D, if you can maintain the plume deflection to less than 1 degree, or 1 degree is about 0.1%. And from the measurements I've done for the bevel 24, the plume deflection is of the order of 1 to 1.5 degrees, and that is without doing anything. So there is a tremendous opportunity here to reduce this much further. And the drag penalty for the same L/D is roughly 0.1%, and I've been told that it will be impossible to measure these kind of small changes on an aircraft. So we can keep the losses to very low levels while gaining extremely high noise benefit at takeoff. Now, there is the other issue of cabin noise. I'm sure all of you flew in from somewhere. I urge you to take a walk from the front of the cabin to the back during the flight. You will notice that the noise continuously increases. That's why you have the cheap seats back there where it is the noisiest. Now, the primary component for the highest noise levels at the back is due to engine exhaust noise, which impinges on the fuselage and gets transmitted through the cabin into the people who are sitting there. And this is the engine exhaust noise is the primary component. Next, you have the aerodynamics noise, which is due to the air turbulent boundary layer on the fuselage, and then you have the ECS noise, which is not a major player there. Let me show you what the bevel 24 does for the cabin noise. Now, for cabin noise, you should be looking at given the engine location, you should be looking at a 90-degree azimuthal angle. And this is a typical cruise power. Black is conventional nozzle, and red is the bevel 24. And I've only picked the angles to the very back of the plane, 140, 150, 155, and 160. Again, you get a tremendous amount of noise reduction of the order of 3 to 4 dB in overall sound pressure levels. This is, again, cabin impingement noise. Some of that gets transmitted into the cabin. We don't know how much of it is done. Of course, one doesn't have to put the bevel at the bottom. One can use to rotate the bevel to reduce or maximize or optimize MOD and cabin noise benefit. Of course, if you have a rotatable bevel, you start with the bevel at the bottom for the community and then rotate it to shield the cabin from the cruise noise. But we can play some games and to optimize this. These are the kind of studies which are ongoing right now. Let me conclude that noise benefit has been demonstrated for turbofan engines at typical engine conditions and takeoff flight Mach numbers. We can get up to about 4 EP and dB benefit at takeoff with a low level of thrust degradation of 0.2%. Plus, with this simple concept, you can also reduce the cabin impingement noise. The beauty of that, it is very simple, easy to retrofit, and that's where I think we can make money, and it involves no modifications to the nacelle. It's only a simple nozzle change to the primary nozzle. So it's simple, practical, and easy to implement, and these are the kind of concepts we need for aircraft applications. And I will conclude my talk there.
in the interest of time, just one question.
Oh,
The thrust loss of 0.2% would be accepted by the customers.
I'm not saying we have to live with this. What I'm saying is, even with you just to take a straight nozzle and cut it straight, you get 0.2%. But we can be cleverer than that and redesign the primary nozzle. The last portion of the nozzle I showed on that 747 engine to reduce the thrust loss. Well, if you can push it to below 0.1%, cannot be measured. So if you can just in the error band, that will be goal too.
Okay, thank you, Vishie.
Thank you.
All right. For coffee break?
Yes.